Greetings, fellow mathematicians! We are going to go through an overview of trigonometric substitution and everything you need to know about it. This video will be split into two parts. The first part will be a general introduction to why we make these substitutions and some steps for evaluating these problems. And then the second parts are going to be all the standard algebraic steps that eliminate the square roots or radicals. So let's get right to what these integrals are and the technique that we're going to be using called trigonometric substitution. And the first thing to point out, this method is a way to evaluate integrals involving square roots or radicals. The integrals have nothing to do with trig functions. So let's take a look at two examples. These are fairly standard for a Calculus 2 course dealing with trigonometric substitution. And notice both of them contain square root expressions or radicals. So our goal is to use a trigonometric or trig substitution to eliminate the radicals or square roots. Now, why would trig have anything to do with these square roots? Well, let's take a look at the most basic square root or radical expressions you can encounter. And we're going to point out that they're going to look very similar to basic Pythagorean trig identities. So let's take a look at the first one, the square root of 1 minus x squared. And take a look at that inside part to the square root that looks like 1 minus sine squared, which we can rewrite as cosine squared. That would be inside the square root. Take a square root of something squared and it will cancel. And we're going to notice that similarity for the radical, the expression inside at least, and how it looks very similar to a trig identity, a Pythagorean identity. The other radicals are very similar. 1 plus x squared inside a square root. That inside looks like 1 plus tangent squared, which we can rewrite as secant squared. And again, using this identity, you'd have a perfect square inside a square root, which would cancel. The last one is really this identity, but rearranged. You can just subtract the 1 to the other side, and we're going to notice now x squared minus a number, or x squared minus 1, looks very much like secant squared minus 1, which we can rewrite as tangent squared. So just make sure you are comfortable with the two Pythagorean identities we're using. We have our basic Pythagorean identity in terms of sine squared and cosine squared, and we're using the one in terms of tangent squared and secant squared twice here, just with terms rearranged. Now, these are the most basic radicals or square roots, where we have combinations of x squared plus or minus 1. Now, what do we do if we have extra numbers in there? Let's say, like we have here, the square root of x squared minus 4. Well, this is where the trigonometric substitutions come in. And for each of these three basic radicals, they generalize to these three radicals here, where instead of having 1 inside, we have another number which we're calling a squared. So here, a is just a real number. Now, the way we start these problems for what's called trigonometric substitution with our steps up there is we basically just make an identification from our radical or square root, and each of those radicals has a corresponding substitution. Now, I hate to tell my Calculus 2 students just to memorize things, but this is one of them. So for each of these three radical or square root expressions, memorize these three substitutions. The square root of a squared minus x squared, that is a sine substitution, x equals a times sine of theta. Square root of a squared plus x squared, we're using the substitution here, the trigonometric substitution, x equals a times tangent theta. And then the last or third radical or square root expression, the square root of x squared minus a squared, we make a substitution for x equals a times secant theta. Now, in red here, I have some intervals written, and that's to properly define here what we're going to be calling in general an inverse substitution. We have to make sure these trig functions, sine, tangent, and secant are 1-to-1. And that's just really there for some technical reasons to make sure everything's properly defined. All right. Now, we'll be getting to how we use these substitutions in a moment to eliminate those radicals. But let's keep in mind the steps that we're going to go through for every single trig substitution problem where we have integrals involving radicals. All right, so first part, make sure you memorize for each of these radicals each of these 3 standard trigonometric substitutions. Now, how we're going to start each of these problems. Step 1, we choose a substitution, a trig substitution, based off the radical or square root. All right, and that's always going to be one of these 3, a sine, a tangent, or a secant substitution. With that substitution, step 2, we plug it in to the expression here, our integral in terms of radicals, and we always use a Pythagorean identity to eliminate the square root. So that's always step 2. That will always happen. And the important part to realize here in step 3, you start with integrals in terms of square roots, but they convert to trig integrals, which was likely the previous lecture topic that you covered. So make sure you're comfortable with trig integrals, powers of sines and cosines, powers of secants and tangents, and all those types of trig integrals. All right, now that's step 3. You use your substitution, eliminate the radicals, and then you are left with a trig integral. Go ahead and evaluate that. Your last and final step is, like all substitutions, you convert back to your original variable, which for our integrals will be x. And there's 2 ways to do this, which we'll be getting to in the next part in a moment. You can convert back to x using what I call a conversion triangle. Basic right triangle, SOHCAHTOA will get you through that, which we'll see in a moment. And the other way you'll convert back to x is possibly also using inverse functions. All right, so make sure before you get to the next part, you have in your notes or memorize for each of these 3 radicals or square roots the appropriate trig substitution, sine, tangent, or secant. So at this point, let's go ahead and get to the standard algebra of how we take these substitutions, plug them in, and get the radical or square root to cancel. Let's start by eliminating the first radical, the square root of a squared minus x squared, with the substitution x equals a times sine of theta. All right, this is standard work for all trig substitution problems. We're going to go through it in detail. So for your radical, start by plugging in the appropriate substitution. All right, so we're going to replace x with a times sine of theta. And that is inside your square root. Next, use properties of exponents to square both a and sine of theta. You'll get a squared minus a squared times sine squared of theta. The key step to getting the square root to cancel and using a Pythagorean identity is we're going to factor out a squared from those terms within the square root or radical. All right, so we're going to factor a squared out inside the square root, and you'll be left with, in parentheses, 1 minus sine squared. And the key step for why this works is we're going to use our basic Pythagorean identity to replace 1 minus sine squared with cosine squared. And that's basically it. If we use that identity, we get the square root of a squared times cosine squared of theta. And if we take the square root of each of those, you'll be left with a times cosine theta. The squares and the square roots cancel out. And we've achieved our goal of getting the radical or square root to cancel. And that will happen for every trig substitution problem, these integrals involving square roots. Now with our substitution, we're also going to create the conversion triangle, which is going to, at the end, allow you to convert from theta or functions of theta back to the original variable x. So let's start with our trig substitution. X equals a times sine of theta. And we're going to rely on just basic right triangle SOHCAHTOA. So let's solve this. For sine theta, we can divide a to the other side. And we'll write this as sine of theta equals x over a. And we're going to think of sine of an angle as the opposite side divided by the hypotenuse. And that tells us 2 of the 3 sides in a basic right triangle. Let's go ahead and sketch that. All right, pretty standard to put your angle theta right down there. And relative to that angle theta, the opposite side we're calling side of length x. And relative to that angle theta, the hypotenuse, we're going to call that a side of length a. All right, now you know what to do from here to determine the third or missing side. You can use the Pythagorean theorem, and if you go through and do that, you'll get the square root of a squared minus x squared. And that is our complete conversion triangle for this trig substitution x equals a times sine of theta. Now, how you're going to use this depends on the trig integral you get and how you evaluate that. But let's suppose in a problem that we're going to have linked down below in the description, let's suppose in your final answer, before you convert it back to x, let's say you had in your answer tangent of theta plus c. If you made this substitution, how would you use this conversion triangle to convert tangent of theta back to x? Well, we can just rely on basic SOHCAHTOA and our conversion triangle. Tangent, that's going to be opposite over adjacent. So if you just use that from up here, for this conversion triangle, tangent of theta, that's going to be opposite x divided by the adjacent side, that square root expression. So we would get tangent of theta as x divided by the square root of a squared minus x squared. And in your final answer, you would convert your function of theta back to x using that. And you might write your answer for that problem as x divided by the square root of a squared minus x squared plus c. And the specific trig functions you get of theta, that depends on the trig integral that you get. All right, so that deals with eliminating the radical for a sine substitution. Let's go ahead and get to the next one, a tangent substitution. Next, let's eliminate the square root using a tangent substitution. The radical or square root expression here is now the square root of a number squared plus x squared. And we use as our substitution x equals a times tangent theta. So let's go ahead and plug that in the same as we did before. All right, and we'll take our time to simplify this since this is standard algebraic work for all these problems. All right, first square each part inside your parentheses there. You'll get a squared times tangent squared. Another standard step, factor a squared out, but within the square root. So we'll get the square root of a squared. And then in parentheses now, 1 plus tangent squared. And the key step to get the radical or square root to cancel is now we use a Pythagorean identity, which always happens. The one we use here is 1 plus tangent squared equals secant squared of theta. And if you go ahead and rewrite that, you'll have the square root of a squared times secant squared of theta And if you take the square root of each part, the squares and the square root will cancel, leaving you with a times secant theta. And that's how the radical is eliminated using a tangent substitution. All right, next, let's use our substitution to create the appropriate conversion triangle from that. Again, basic right triangle, SOHCAHTOA. Start with your substitution. And let's go ahead and solve for tangent. Divide a to the other side to get tangent of theta equals x over a. And now if we think from SOHCAHTOA, tangent of an angle, that's going to be the opposite side divided by the adjacent side. And we can create our right triangle with two sides from there. So again, draw your standard right triangle. Put your angle theta down there. Don't forget the right angle. And relative to that angle theta, the opposite side, we're going to denote it to be of length x. But now the adjacent side, that'll be of length a. All right, and you can see what to do from here. Determine the third side using the Pythagorean theorem, and you'll get that it comes out to the square root of a squared plus x squared. All right, and that is a complete conversion triangle using the tangent substitution. Let's get to the last part, a secant substitution. Next, let's eliminate the radical or square root using the secant substitution. The radical here is now the square root of x squared minus a squared, and we substitute x equals a times secant theta. All right, let's go through the steps for that, since you'll be doing that for all these questions. So we're going to replace x with a secant theta. All right, you know what to do from here. Square each part in the parentheses. You'll get a squared times secant squared theta minus a squared. And again, you know what to do. Factor out a squared from within the radical or square root. If you go ahead and do that, you'll get a squared. But now times, not 1 minus something, but rather secant squared of theta minus 1. And here, inside those parentheses, we make use of the second Pythagorean identity, but rearranged, secant squared minus 1. That equals tangent squared. And if we go ahead and put that in, we get the square root of a squared times tangent squared theta. And again, take the square root of each part, and you'll get the squares and square roots to cancel, leaving you with a times tangent theta. All right, again, all the work here is fairly standard. Plug in, factor a squared out, use a Pythagorean identity, and then get the square root or radical to cancel. Now, the work for the conversion triangle here is a little bit more involved, since you have a substitution that's not basic in terms of sine, cosine, or tangent. Let's go through that in detail. The substitution is x equals a times secant theta. We'll solve for the trig function, secant of theta first, divide a over again. So we get secant of theta equals x over a. And I always like to think in terms of sine, cosine, or tangent. So let's rewrite secant as 1 over cosine. So we get 1 over cosine of theta equals x over a. And we're basically going to flip that, and we'll get cosine of theta equals now a over x. And that allows us to now determine 2 of the 3 sides. Cosine of an angle, that's going to be the adjacent side divided by the hypotenuse. So let's determine our conversion triangle from here. It can be done with secant, but if you remember basic SOHCAHTOA, now you can apply it here. So if we go ahead and fill that in, we get a right angle, theta down there, and relative to our angle theta, cosine of an angle, is going to be adjacent. So now A is here. But notice your hypotenuse is now x. And as always, the third side can be determined with the Pythagorean theorem, which here comes out to the square root of x squared minus a squared. Definitely work that out. It's a good exercise. All right, this is all fairly standard. The very last thing that we need to get to, which we'll get to in the next part, is how we convert everything from an integral involving radicals or square roots to a trig integral. We're making a substitution. We need to calculate a differential. The last thing that I want to point out, which we're going to need for step 3, converting from the original integral to a trig integral, is for each substitution, we calculate the differential dx. The good news is you already know all of these trig derivatives. So let's go through the first substitution, a sine substitution. The derivative of sine is cosine, so we get our differential dx for this substitution to be a times cosine theta d theta. For your tangent substitution, you know the derivative of tangent, that's secant squared. So dx here comes out to equal a times secant squared theta d theta. And then for your last substitution, which is a secant substitution, you also know that trig derivative. The derivative of secant, that's secant times tangent. So your differential dx here works out to be a times secant of theta times tangent of theta d theta. And this is a very simple but often overlooked part of how you convert in step 3. So your standard steps here, choose your substitution, plug it in to eliminate the radical using a Pythagorean identity, but to properly convert to a trig integral in step 3, don't forget to calculate and plug in the differential. That makes all the difference in getting a very simple, correct trig integral, or one that might be impossibly difficult, maybe because you forgot some factors here that might cancel out. All right, this again is a short overview of everything you need to know about trigonometric substitution. Definitely refer back to this as you go through problems. It should help you through them, which I'm going to have linked down below in the description. Hope you enjoyed the video. If you're enjoying the content and learning a lot, support the channel, like and subscribe.